the video for 1.3, and I'm featuring my cat. See my cat? Cat. Oh, okay, well, he's not looking, but we just came off of our project of doing a best fit line, or also called lines of regression, with linear equations, and I wanted to go back to 1.1, which was just dealing with equations and relationships between variables. And what I did was looked at number 76 from that 1.1, and there was a flaw in the 76. They gave us that equation, and we were expected to just work with that equation to figure out things about the future, make predictions about the future. What they did was they only used data from the year 1980 with x being 0 up until the year 2000 with x being 20. So because, let's face it, our books are a little bit outdated, the books were published in 2003, that's all the data that they had. So you can see that this red line it was a fairly close fit to the data that we had. And by the way, I have the adjusted U.S. federal debt plot points, and I got them from this website down here. But you can see that that red line, they could have done better, but that red line is the best fit line that they came up with for those data points. What I went ahead and did was I adjusted that model that they came up with for this situation, and I came up with this black line. So I guess the thing, we're just awesome. We've been modeling real-life situations here because that's what we can do with our mathematics. I wanted to just kind of make the point that as you collect more data, what you thought was awesome for a model might not be as awesome as you thought, so you'll just have to go and adjust. And that's just what happens. Alright, so with that, we're going to look at 1.3, which is dealing with functions. And our objectives are to understand the implications of a function. So we have this whole realm of equations, or this whole family of equations that are out there. And then what we can do is look even closer at a set called functions. So within those equations are what we call functions, and we're going to start looking at those. And we need to figure out what exactly puts an equation into that smaller set. Who can belong there? Find the domain and the range. That's something that's important with functions. And then use function notation. Notation is just symbols, really, to symbolize some sort of meaning. Like we have letters to symbolize and notate sound. We're going to have these symbols to notate and label that there's a function involved, or that we're dealing with that small set. Alright, here's where you are going to be writing down some vocabulary words. The biggest thing that I want you to focus on is that it assigns exactly one output to each input. But otherwise, what you'll notice is the function definition is a lot like an equation, because again, a function is an equation. We said that equations are just those relationships between, especially the two variable equations, they're the relationships between two variables. And of course, they don't always have to be x and y, but we're just saying that there's an input and then there's an output. So that is the definition of an equation, but we have this added on. Domain. Now, here's the thing about domain. It's important because just like, let's say, a toaster, for example. With the toaster comes the warning of there's only certain things that you can put in this toaster. For example, you may not want to put your finger in it because you get electrocuted, but you certainly can put bread in it and a bagel and things like that. So with these functions, we're going to be just like the toaster. We're going to be saying that there are certain values that you can and should not plug in, or you can't plug in, or you'll come across problems. So looking at that with a mathematical standpoint here, I have this equation here which does happen to be a function, and we'll visit why in a little bit, but this is actually a 3-variable equation, and it happens to represent the volume of a cylinder with respect to the radius and the height of it. So since I only want this to be 2-variable, I'm going to go ahead and set the height to 3. So here is where I have now my 2-variable equation. Oopsies. So, I was going to do this. Okay, if you graph this, this is not going to be perfect, but if you did this on your graphing calculator, or whatever. This is not perfect, but I do know that it's a quadratic, so it's going to look something like this. Okay, where we have r is our independent, that's the radius, and depending on whatever radius is, whatever the radius of that cylinder is, then it's going to have a certain volume. So what I'm going to do is that forewarning of don't put your finger in the toaster, or in other words, what we don't want in this function are r's that are negative, right? And I'm going to say technically we can't have 0. You're just not really technically going to have a cylinder with a volume there. So I'm going to say that the domain, and I'm putting that warning out and just that information out, that the radius has to be greater than or equal to 0. That would be my domain. Alright, so that knocks off all of these values over here that would cause you kind of a problematic idea about what's going on. So range, it's a lot like the domain, it's just that warning of expectation. The range here is going to be the set of all possible outputs though this time. And then same thing kind of since we're dealing with volume and radius, volume can't be negative either, and you can see that in the graph that we have over there, volume is also going to be greater than or equal to 0. Okay, so it's just kind of that expectation for people. Functions. So how do you figure out who belongs in that function family? So I'm going to go ahead and say that polynomials are things to look out for. Alright, poly means many. I will also say that there could just be one, technically. So they're one term or many terms consisting of a coefficient non-zero. So the coefficient's the number out front. Why can't it be 0? Obviously you wouldn't have a term there. A variable, and then a non-negative integer, which again, an integer is just a whole number, exponent. So looking at this down here, we're just going to determine is it a polynomial or not. So here we have many terms. It fits all of these. Technically there's a 1, a whole number exponent there. And then you're wondering, what about the variable? There is a variable, and it has the exponent 0 we could place there, but anything to the 0 is just 1, so that would just be 1 times 1, and we don't write that because that'd be weird. Okay, so there's a yes, that is a polynomial. This right here isn't separated by any addition and or subtraction signs, so this is just a 1 term, which is okay, it can be 1 term. But if I were to rewrite this, the radical can be rewritten to the 1/2, and this is where we run into the integer issue. This is not an integer, it's a fraction, so this is a no. So I just want to put one little thing out there that might be a little confusing, so take a moment to try to absorb it. This is not a polynomial, but at this point in time we cannot say that it's not a function. It's definitely not a polynomial, but again we have all these equations, we have this small family inside. Some of those equations are polynomials and we can say they are functions. But there's other things involved too, so just because this number 2 is not a polynomial doesn't necessarily rule it out of being in that family. So just consider that. But I just want you guys to be able to know if it's a polynomial or not. 3 is also a polynomial, and this, yes, it's only 1 term, but this is also a polynomial. Alright, rational, they're just the expressions separated by division or a fraction symbol. So anything that's a rational function like this, rational equation, can be placed as a function as well. And then we'll get more into this, but there's a whole slew of what we call parent functions, and they need to be recognized as functions as well. They are things like quadratics, cubics, there's others, absolute value, but we'll get into that more. So there's a whole slew of things that can be functions. Like I was saying, absolute values, y equals cubic. Oh, it's not writing. My computer just froze, so I'm just going to hope the next slide will work better. But there's, again, the small family that we call functions. Every function is an equation, but not all equations are functions, and in the next slide we'll say why. An equation that's not a function would be a circle, for example. So we have equations out there that are not what we call functions. Alright, requirements and implications of the function. So if you are in that family, what does that mean? If you are a function, what does that mean? And the biggest thing here, as you saw in the definition, is that for every x value, there is only one y value. Good, it's working again. So I'll get into that more, but that is the biggest thing. What's nice about that is it makes these functions of study predictable. It's not going to do something like do and then all of a sudden curve back on us for multiple output values to one input. So this input of 3 in this case has 2 values, and it's not going to like do anything weird like that to have many outputs. So it makes it nice because we can expect certain shapes and we know that they'll continue on the way that they're going. The nice thing also when we're saying predictable is it produces nice outputs for us. So when we model something such as the federal debt, like I did at the slide at the very beginning of this video, the idea is if I asked you a question of what was the debt in 2010, it's not like I would provide 2 different answers for you to leave you confused and saying, well, which one was it? Was it 1.1 billion or was it 3.2 billion? It's just one answer, so it's going to be one answer. It's a nice clean answer, so that when we create these models for people in the business world, our models aren't going to be giving them all sorts of crazy answers, just one. So the method for determining if a function fits in that family or if an equation fits in that family that we call a function is typically what we would want to do is recognize is it a circle or not, because circles are probably the best example of something that's not a function. The other thing is we can solve for y, and then what you would want to do is see is there a plus minus that shows up, because if that's the case, let's look at an equation like this, y equals plus minus x. If you were to input 2 for this, well, y is equal to not only positive 2, but then y would also be equal to negative 2. So you just created something that's confusing for that player. Well, when I input 2, is it negative or is it positive? Well, it's both, and that can happen with functions. And then fails the vertical line test. We're going to get into that in the next slide a little bit more, but in this case we had 2, which was positive 2 and negative 2, so that's our graph at this point, and right at that 2 is that problem of not passing the vertical line test. And all that is when you draw a vertical line, it needs to cross the graph that you have drawn only one time. So let's do examples of this. Let's determine whether the equation represents y as a function of x. So is this equation, if we solve for y, a function of x? So I'm going to go ahead and solve for y. I have addition and this exponent to get rid of. Remember, we're doing the reverse order of operations. So I'm going to subtract off this chunk first. So we have y squared equals 4 minus x minus 2 squared. And then when I square root, don't forget when we square root, we have a plus minus that shows up. So those 2 things that we had to watch out for, besides the vertical line test, was to watch out for that plus minus. So this is not a function because of that. If you were able to see that this at the very beginning was a chunk plus a chunk equals a number, this is a circle, okay, that right away would rule it out as a function. So if you, and just to kind of show the vertical line test and its involvement here, we know that this was the x minus, and then whatever that number is the x value of the center. Y minus technically 0 here, so 2 comma 0 is my center. Okay, and then this right here is our r squared. That is our circle equation. Again, like I said, that's important for you to be able to identify. There is our circle, and then clearly this does not pass the vertical line test. No. Okay, so these are what we call set diagrams, and sometimes they're a little confusing, so I'm actually going to just plot these points. We have the domain, which are the input values. So negative 2 is attached to 3. And this is where that becomes confusing because you're looking at this and thinking, is that okay? Oh, are these okay? These are actually okay that -1 and 0 are attached to the 4. -2 and -1 is attached to the 3. But what's not okay is this -1 being attached to both 3 and 4. So this is where we have the issue. -2 is attached to 3. -1 is attached to 3. -1 is attached to 3. That's okay. Still passes the vertical line test, but now that -1 is also attached to 4, bad X. You just failed the vertical line test. So this graph right here, no, this is not a function. Alright, some more. Determine whether the equation represents y as a function. So here I'm going to solve for my y again. And when I do, I'm going to get the plus minus. And that right there rules you out. So no, not a function. This, again, I'm going to do the same thing. I'm not recognizing it as a circle. I don't see any plus minuses yet. So this is hopeful. So I'm going to subtract off the 2x, subtract off the 2x. I technically have 4 minus 2x, but I'm going to write it like this. We have 3y, I'm going to change this to plus negative, equals, and then negative 2x plus 4. Because addition is commutative, we can just swap those terms around. Divide by 3. What we have is this whole side divided by 3, so -2/3 x plus 4/3. This right here, we have no issues with plus minus. Hopefully you see this as y equals mx plus b. This would just be a line if you were to graph it, and this passes that vertical line test, and therefore it is a function. So notation. How do we notate that something is a function? Because right now I'm looking at this and it's just an equation to me. So what we do is we'll often stamp it as a function by using this notation right here. You can also have like g of x, h of x, v of x. It doesn't matter. It's just this kind of letter with the parentheses around the input values. So that's what we have. And to visualize this, I have a stamp. So I'm going to stamp myself. Ta-da! What the W stands for? Well, weird. I mean, why would I say that? Winner, of course. So now I've stamped myself clearly as a winner so that everyone can see it, and then they just know. It's not a question, they just know. So here's a more math-related example. If you looked at something like this, you would be saying, here's the equation that we just looked at, and we know that it's a function, but by just looking at it, it's not very clear. So this is where you would just go ahead and, just like I could stamp myself to clearly indicate to everyone that I'm a winner, you can go ahead and stamp this to clearly indicate to everybody that it's a function. So now everyone knows there's no question. Let's just look at why this notation is so nice. Before, when we were looking at equations, we could look at something like this and just say, well, here is the equation. Solve for when r is equal to this, r is equal to this, r is equal to that. Instead of looking at it like that, what we can do is give the notation. We know now, because of that stamp, it's clearly a function, and then you can just write v sub r. So that's how we read it, because what it's saying is take that function given and sub in r. It's saying, or sub in 3. It's saying that we're wondering what is this function equal to when that input value is 3. So this is where we would just go ahead and sub in for where that r is, exactly where it is. I like to draw parentheses around it. Sub in that value. So this does say to evaluate the functions as specified values of independent variables. It also says to simplify. So this thing right here is equal to 36 over 1, but I'm not going to write that. Pi. Down here, same thing. We're going to just exactly know what to plug in. And this final one, there's still a variable in it. That's okay. What's for r is going to be put in as 2r. That's what it's saying. So I did that to the third, and this also distributes to each of those factors inside that parentheses or inside that group. So we get 8r to the third, and then we could go ahead and distribute, reorder. 32 is what we get for the 4 times 8 pi r cubed, and that's as far as we could go with that one. Alright, find the values of x for which f of x is equal to g of x was the directions for this number 51. I'm not actually going to do this problem, but I'm just going to help you interpret it. I mean, when you read out the directions kind of slowly, maybe it might seem a little bit more meaningful to you in what you're supposed to do, but we want values for x when this equation is equal to this equation. They just so happen to use the function notation. When is this function equal to this function? If you were to graph this, I'm not really sure what it looks like. I know it's a quadratic, but maybe it's something like this, and then we have a linear equation that maybe looks something like that. You're trying to find those x values for when the functions are equal, so when they intersect, really. How are you going to do that? I'm going to leave that up to you. I'd like to see what you try. We'll discuss that tomorrow in class. This one's a little bit long, so take the time to write these notes down. So we're diving a little bit more into the domain. And again, those are all possible inputs, like we were saying with the toaster. What can you expect to be able to put in? And to communicate to people what you can put in, I'm going to be asking you to use what we call interval notation. So it's going to tell people what are the values possible. And what we use is we use a set of these brackets, and just to kind of let you know, I mean, we're going to have from a low number to high is what we do, and then you're going to pick and choose which set of brackets to use. So it could be square brackets, it could be rounded brackets like I have here, it could be a combination where there's one square and one bracket. But what we were discussing earlier was when we had that cylinder problem and we had that the radius had to be greater than or equal to 0. Instead of me communicating to you that the domain is greater than or equal to 0 by using these inequality symbols, what I'm going to ask you to do is to use these interval notation symbols. And this, if we were to graph it, would look something like this, or plot it on a number line. We have a 0 here, and I'm going to draw a dot at that 0. That's my smallest value, and then I want everything that's above it, so everything to the right. That's how we would plot it. Okay. So what we do to indicate what this stretch of numbers is, we would say, well, the smallest or the lowest number here is 0. 2, the highest number goes on forever. That's when you can use infinity. If we did have a cutoff, like let's say the radius could only go to 100 because that's the room that you had for that cylinder. If you had the radius up to 100, you would have said this was the highest point, which would be 100. But we can go to infinity here. It is a closed dot, or it includes the 0, so this is when we would want to use the square brackets to include a value. And I am always going to use rounded brackets around an infinity symbol because you can never really include the value infinity because it's unreachable. You can't really claim that number. Alright, let's say we had something like this where r was just greater than 0. We didn't want to include 0. So instead of using the square brackets, we would use the rounded brackets. Okay, so just use that, and that would not include that value. Alright, if let's say you could put all real numbers in, well, the lowest number you could put in is negative infinity, and the highest number would be infinity. Alright, and then the biggest thing is when we're identifying the domain, things that we have to look for are radicals. Because radicals, what we do know about those is the expression underneath the radical cannot be negative, right? So I'm going to just write that. The expression under radical needs to be greater than or equal to 0. What I mean by that, we can do an example. Sorry, I'm squashed on space here. If we had the function, let's slap in that stamp there. F of x is equal to, and then x, let's say minus 3. Right? We could plug in 3 and be okay, but let's say I went ahead and unknowingly didn't know I couldn't put my finger in the toaster, or didn't know that x could not be something like, let's say, 1. Let's go ahead and figure out what is f of 1, and when we were to plug that in, we would have this thing going on. And I don't know if you guys recognize this, but this is problematic. It would be that point where you just got electrocuted or zapped by the toaster. This thing is not allowable. Well, it technically is, because it's what we've traveled into the imaginary number realm. So in order to just warn people of that, what we would want to say is, well, watch out, because what's underneath this radical, that expression, x minus 3, needs to be greater than or equal to 0. Let's solve for x. I'm going to add 3 to both sides. And when you do that, we would get x is greater than or equal to 3. So this right here is the domain that you're indicating to people. But what we're going to go ahead and say, because I'm going to be picky about this, is we have 3 here and we want all values this way. So instead of writing it like this, I'm going to say our lowest number that we could do was 3. Up until infinity, I did use the square brackets around the 3 to include it. I used the rounded around the infinity because you can't include it. Rational. Remember, rational expressions are when we have a numerator and a denominator. What I'm going to say is the denominator, you need to indicate to people values such that the denominator does not equal 0. Remember, if you ever have something on the bottom that equals 0, it's undefined. So let's look at this function right here. F of x is equal to, and then we'll say x plus 1 over x. Keep it easy enough. So you're looking at this and you're thinking, x will not be able to equal 0, because otherwise we would have 1 over 0 issue. You just got electrocuted. So what we would have to say is x cannot equal 0. Now how are we going to indicate this in our interval notation? Well, on the number line, this is what it would look like. We would have 0 here, and then I'm going to put a dot, but it could be all of these values and all of these values. So the lowest value from in negative infinity up until 0, that's one stretch. I am going to put rounded because I do not want to include that 0. And then you would just go ahead and continue on from there. We're going to say 0 to infinity. So what we've done is we've basically, just right here, broken that stretch of numbers at that 0. We've taken that effort to disinclude the 0. Watch out for radicals, watch out for rationals when you're looking for a domain. I'm actually going to erase this, and I should have written these down. Alright, and I need to make a correction on what I just said. So I made the correction here. Please go back and adjust this that have even radicals. When you have an even radical, that's when you have to watch out for expressions under the radical needs to be greater than or equal to 0. Okay, those ones are the ones that need to be greater than or equal to 0. You don't have a problem with even, like you do if you had something like this, -1, that's a problem. Alright, you're going to even try it in your calculator, not going to work. But if you had something like this, y is equal to cube root of -1, this does work. There is, it's asking you what times what times what is equal to -1. Well, -1 times -1 times -1 is equal to -1. This is saying what times what times itself is equal to -1. There's nothing you can do to get -1, right? You could try -1 times -1, but that gets us just positive. So because of that even nature of the exponent. So this right here, it's okay when you have odd number radicals or odd roots to have negatives. So in this case, this is actually going to be all real numbers. You do not have a problem. The things to watch out for didn't exist in this problem. for life.